Hey, what's up, Franklin West? I have another video for you today. This one is still about solving linear equations, but how do you recognize when it's infinite solutions versus no solutions? And so this is an extended topic at the BFA Fairfax Math 1 class, and I hope that you find it helpful. And let's hop into. Here is a super big, impressive linear equation that we are going to steadily break down into its parts and simplify. And so we are in the I totally got it, I'm ready for more category, the extension. And so I'm going to spend less time explaining things so that we can get really to the meat of this. So if you chose this level wisely for you, hopefully that feels like a perfect fit for how I described how I will proceed here. At any point, feel free to pause the video because you can actually create all your work before I do, and then you can compare your steps after when you start replaying the video. So we have 6x minus the quantity 4x plus 5 minus 7 times the quantity, or negative 7 times the quantity, either way. That is negative x plus 3, and all that is equal to 15x minus 36 minus 2, all times 3x minus 5. And so the left is just as busy as the right, but we're going to go through and do all of our distributions. Here's a distribution, and there's another one, and here. And we're just going to do everything that we can on both sides in this one line. So we're actually going to take care of many different things at once. And I challenge you, if you're really feeling confident in this work, see how many things you can do in one line without violating the rules of order of operations. Okay. So we have here, let's get into it, 6x, which will be unchanged. That will just come straight down. I have a negative here, which in our last videos, we said there's a 1 hiding in here, or you could imagine this as the opposite of everything within, right? So we're going to distribute here. But I also said we weren't going to spend a lot of time describing it. So we're just going to follow that pattern throughout all of these. So a negative times positive 4x should get me a negative 4x. And then a negative times positive 5 should get me a negative 5. So I'm just going to have a subtract 5 there. Then I'm going to distribute the negative 7. So I do want to point this out and remind us all that we can't just distribute the 7. It's a negative 7. So even though we can read that as subtract 7, we've really got to take the whole quantity. So every number, the sign in front of it belongs to that number. So we cannot ever separate them. So negative times a negative is positive. So we have positive 7x. And then negative 7 times positive 3 is negative 21. All right, looking good. So now let's clean up the right. So that 15x will come down unchanged. We've done nothing with it. Certainly is true for the negative 36. And now we've got to distribute negative 2 into this quantity. So we should generate a negative 6x and a positive 10. Excellent. Okay, we'll do a quick scan. Make sure we did not leave out any variables where they should be. Everything looks accounted for, looking good. Okay, so now we're going to take a look and realize we've got a slew of like terms here. So those are like terms. We've got x's over here that are also like terms. We'll just clean up on all sides at the same time. And this negative 5 will combine with negative 21. And on this side, we can clean up the negative 36 with the positive 10. All right, so we're going to get to work. Okay, so 6x minus 4x should leave us with 2x. 2x plus 7x gets us 9x. So we were able to combine 3 terms in this one. And now negative 5, subtract 21. You could also think of it as negative 5 negatives and 21 negatives, and together you have a collection of 26 negatives. So what's interesting about a negative subtract a number is it actually is an additive result, because that's actually subtracting a positive 21, you could think about, or you could think about it as adding a negative 21. Whichever way your brain likes to grasp onto that is the way you should think about it. So now we've combined our constants and our variable terms. So now let's go over to the right. 15x subtract from this sign. 6x becomes a 9x. So this is curious. 9x and 9x are on the same side. And then I have a negative 36 adding a 10 to it. So that is making me move closer to 0 from negative 36. So I'm going to be less negative. I'm going to have a negative 26. So even right away, as you take a look here, the left is exactly identical to the right. And this should be a little curious, or at least catch your attention for a moment. If you've seen these before, you might know what's coming. And if not, let's just keep going with the protocol and let's just see what happens. So we're at the part where we're undoing, because we got to combine like terms that are on opposite sides of that equal sign. And so if that's a negative 26, well, then I got to add 26 here. I need to create a 0, right? I'm trying to make that term move to the right-hand side. But notice what happens here also. I get another 0. So the operation ends up being the same. So that's gone entirely. And now I'm left with 9x equals 9x. Well, guess what? These two are like terms across the equal sign, and they have to be consolidated just like we did the 26. And so this right here is a positive 9x. And so in order to undo that, we're going to subtract 9x to both sides, or from both sides. And so what's 9x minus 9x? Well, it's 0. And interestingly enough, we get that on the other side also. So here's what happened. We lost our variable altogether. It just fell away. It canceled itself out. It's gone. And so what also we have here is that we did create something that is true. 0 does equal 0. And so how do we interpret this? Well, let's play back up here in this area real quick. What if I said x was 0? Well, then I'd have 9 times 0 is 0. Subtract 26 is negative 26. So then this would all equal negative 26. And that would be true over here too. So that would be true, right? X could be 0 because left side would equal the right. What if x was 3? So if I made x 3, then 9 times 3 is 27. 27 minus 26 is 1. Same thing over here, 1 equals 1. And so what you're finding is you could make up any number from your number line, a whole number, a fraction, a decimal, a positive, and negative. No matter what you put in for x, it will always make a true statement. And so therefore, this is all real numbers, okay? So the answer here is all real numbers, or we could say infinite solutions. Okay, now why can we say that? Just to recap here, it's because the variable disappeared and because the left did equal the right that we can now say this big statement that it is all real numbers or infinite solutions. So no matter what you put in there, it's going to be a true statement. So there's infinite solutions as an example. Let's keep it in the same video and we'll slide over to the right. This other problem has actually two things going on for it. One thing that we will realize as we go, and the other is how do you solve for x when it's in the denominator? Okay, so I won't make it overly complicated, but you could, I'll talk about one way and then just show the other way. So right away, this is a proportion. You have a fraction set equal to a fraction. And the beautiful thing about proportions is you can flip them. So for example, we could rewrite this to be 4 times the quantity x plus 3 on top with 12 on the bottom. But if we flip this side, we have to flip the other also. And so that would be x minus 3 all over 3. And so sometimes just getting the variable in the numerator of a fraction is more visually comfortable for us. And then we feel like we can dive into the problem. So if that's true for you, or you just want the challenge of trying to take on what I described, then go ahead and solve it that way. And then compare your work to how we do it here. So I'm just going to leave it as is. And remember, we're still in this process of undoing. And so right now I have a 3 that is being divided by a quantity of x minus 3. So this quantity and that quantity, they have to move together. You cannot separate them. And so this is a little different for sure. So let's see how we do here. Okay, so if I am dividing by x minus 3, well, the way I undo that is to multiply by x minus 3. And because I did this on the right, I've got to do this on the right, on the left. Notice the way I'm showing this, it's more of a side-by-side placement in our notation rather than underneath like we've been practicing. And so that's okay. Sometimes it happens that way. So if this was all one fraction, we'd have x minus 3 divided by x minus 3. And because they are exactly the same quantity, they'll cancel each other out and create a 0. They'll create a 1. That does not happen over here though, because x minus 3 and x plus 3 are not the same. Okay, so let's rewrite what we have here. Remember, this is on the top. So if it helps you, you could think of these as over 1. So that way you can fall into your reliable skills of multiplying fractions. So numerator times numerator over denominator times denominator. So this will get us 12 times the quantity x minus 3 all over 4 times the quantity x plus 3. Now, I chose not to distribute this yet. You could. It's kind of similar to moving things as a big package versus individual items. So I think when they stay this way, you can clearly see it as a package that has to go together. Whereas if you distributed the 4, it looks even more complicated than this one. And so you might be prone to error. Okay, and then look at what we did here. We cleaned up the right-hand side, right? There's just a 3 over there. It was 3 times 1, so that's 3. So we're going to use the same process because the goal here is we can get much more done if we can eliminate the need for the fraction bar. And so see how we cleaned up the right-hand side by multiplying by the denominator? We lost the having to deal with the visual of the fraction. So here, this quantity is being divided by this quantity. And so if I want to undo that division, well, I'm going to multiply. So, and actually this one will make it more of a bracket because we're going to, anytime you go to do this work, you probably want to put in parentheses what it is you're going to multiply by. That way you don't miss your chance for distribution. Because without it, you might accidentally do a partial distribution and not even realize you were supposed to do a true distribution. Okay, so we remove this as a whole package. So if I'm dividing by 4 times this quantity, well, let's multiply by that. And so now you get a chance to see this over this cancels out as 1. So that's gone. See how that's going to help us simplify the left. But this side will get a little more complicated, a little more expanded compared to how we left it in the prior problem or the prior step. So let's see if we can clean this up. So we've got 12, whoops, I'm going to redo that one, times the quantity of x minus 3. And that is equal to here. So we could do this in a few different steps. I'm just going to work most inner. That way we don't risk violating any PEMDAS rules. So I'm going to keep the 3. And I'm going to distribute the 4 to the x and the 3. So I'm going to have 4x. Again, if you had done this earlier, then you don't have to do it here. So this is where our processes might look a little differently if you did the distribution at the start. So I'm going to get a 4x plus 12, and I'll distribute that 3 in there. So now I've got a 12x plus 36. Okay. Now let's distribute over here. I've got a 12x minus 36. Okay, so if you're thinking about how this compares maybe to the problem we did on the left side of this board, we got an interesting case in front of us right now. We got 12x and 12x, we got 36 and 36. However, those are opposite signs, okay? This is not exactly identical. So even at this moment, if they were exactly identical, even in signs, you would know it's infinite solutions. You should still show the rest of your work to prove it, but hopefully you can gain the comfort in recognizing infinite solutions when you're on the pathway. If that way you don't have to wait until the moment that you have infinite solutions, you'll know the whole time. So this case is a little different, but we're gonna continue as we do to undo in order to combine like terms across the equal sign. So on the left, I get the 0 canceling, which is by design, right? We're trying to have that disappear. But over on this side, that's going to combine to a number that's not 0. So let me scroll down a little bit. So we are going to have 12x on the left is equal to 12x. We haven't changed yet, so there it is. And then 36 plus 36, that will end in a 2, so plus 72. Okay, excellent. So, and actually, I realized in the work that I have next to me as I prepared this, we could have taken care of this 12 right away and not have all these big numbers. So if you caught that we could actually reduce coefficients at the beginning to simplify the size of our numbers, then that is awesome. Good for you. Okay, so now we've got this. We got 12x equals 12x plus 72. Right away, this should catch your eye. This should be like a 5-alarm bell ringing. How could this even be possible? If x is the same value, then these two are identical. How could adding more help keep these to be the same? And so we're going to try to isolate to get all the x's on one side and all the numerical components on the other. And so watch what happens as I try to move the x terms to consolidate them. I create zeros in both places. And so now I get something that is crazy wild. I get 0 equals 72. And what do you think about that? Not possible. 0 can't equal 72. They're completely different values. And so the variable did drop out just like the last one. However, we created two sides of the equation that are not equal to each other. And so this is a false statement here. And so what we have here is that the answer is no solution. There is actually no value of x you could put in here, and you probably saw that in this line, that could make this equation true. The left will never equal the right. And so this right here, when you compare this one to this one, hopefully you have clarity on how this was identical. This was very close but opposite in sign, and they both have different outcomes. So I challenge you to find more practice like this in your work from your teachers or online. You can always Google search or Safari search, practicing solving linear equations with infinite solutions or no solutions, and there's a wealth of resources out there, even with answer keys, so you can check your work and build your confidence. So well done, folks. Have a good one. So I hope that video was helpful in helping you understand that content. If you are interested in knowing more about this or another topic, do not hesitate to reach out to me. You can always email. If you have YouTube permissions from your parents, you can comment below and tell me what topics you would like to have added into my video list to help you with your continued math learning. And don't forget, if there is science stuff that you need some help with, I can work on providing materials for that also. So I hope it was helpful. Good luck in all that you do. You're all wonderful people.